Okay, this week in chapter 3, we're going to talk about solar radiation. So, what we're really emphasizing here is the fact, where does the Earth get its energy from? The Earth gets all its energy that it powers all the weather, starts at the sun. So, we've got to learn a little bit about the sun and understand some of how that energy gets here and then how it transfers around the Earth before we can really move into meteorology. So that's going to be our discussion this week. So let's see if we can move forward here. So how does this make a habitable planet out of Earth? Well, we need to learn a little bit about macromagnetic radiation. There is electromagnetic and magnetic, and they come in like radio waves when you listen to the radio. I don't know how many of you do anymore. AM radio has longer wavelengths. FM radio has shorter wavelengths. Microwaves, they have radiation. They heat your food. The sun, X-rays that we all sometimes have to need, are all different forms of waves, electromagnetic radiation. So you can see here the sun's waves, visible light, pretty small spectrum of what is a whole large area of electromagnetic radiation. So what is a wave? All right. Wavelengths go from one crest to the next crest of a wave. I like to think about it in an ocean. The waves coming in at you in an ocean, you get one high wave, then it goes down the water, then it goes back up to the next higher wave. That distance between the two crests is a wavelength. Now, all electromagnetic radiation moves at 186,000 miles per second, roughly the speed of light. So that means that when they're shorter, they're still moving at that same speed, so waves are really passing you really fast. When they're longer, you don't get quite as many. So the fact that there is a whole bunch passing you means they're going to have more energy. So the shorter wavelengths have more and more energy with them. All right. With that, almost everything in some form is a black body. Your body, the lamp post out at the school, whatever. When it gets to a constant temperature, it is absorbing almost all the radiation that it receives that's hitting it, and then it's re-emitting that same radiation, but at a different wavelength. So, interestingly, the most intense radiation emitted by a black body is proportional to its absolute temperature. Think about it. The sun's absolute temperature, way high. The Earth's absolute temperature, pretty doggone low compared to the sun, right? So the difference in wavelength is huge between the two. That's why the Earth's wavelengths are called infrared, because they're longer wavelengths than the sun's, which are ultraviolet. So here is that actual chart showing the speed of constant of proportionality divided by the absolute temperature to get an idea. And you can see the visible light actually corresponds pretty doggone well to the sun's radiation. And infrared is a little bit less wavelength, ultraviolet, and they both base on, if you'll notice, reds are to the right and violets are to the left. So ultraviolet has a shorter wavelength, violet has a shorter wavelength than does a red. The next one is how much energy is coming out. Well, it's proportional to 4 times the temperature. So, in other words, it's temperature times itself, times itself, times itself. So, think about that. If the sun's temperature is way bigger than the Earth's temperature, this amount of energy coming out from the sun is much, much, much greater than that from the Earth. Now, as we move away, we make the assumption that, okay, right here we're going to call it 1 astronomical unit from us to the sun. So, if Mars is a little bit further out, which it is, And say you had something that's the radius of that unit, instead of being 1, is now 2, well, the amount of energy reaching that planet would be 1/4 the amount because it's squared. So if that planet was 4 times away from the sun, 4 times the distance from the sun as the Earth is, it would be 1/16. So you can see very quickly the amount of energy reaching the outer galaxy parts of our planets on the solar system really reduces quickly. Now, solar altitude. Well, sun comes in, it's directly overhead at noon. So, where is it directly overhead at? Oh, it's probably, if it's somewhere down towards the equator, is where it's most direct. Now, with that being said, on the equinox, it is directly over the equator. So we'll display that this is the equinox, spring or fall. The sun's directly overhead at the equator. Solar angle, 90 degrees. Powerful, very intense radiation hitting a very small area. But now you go to the North Pole, well, that angle all of a sudden a whole lot different, or 80 degrees north. Notice how the area that same sun's energy is hitting is covering a much broader area. So it's spread out. It is not as much energy reaching that over that area as it is by the equator. That makes a difference in how our Earth is heated. So we can look at that, and we can see even right on equinox, the sun is just barely rising on the North Pole, maybe, depending on which one it is, or the South Pole. And you can see the angle here, much broader area that the sun's radiation is striking over. So not as much radiation is reaching that part of the Earth. And when you look at the solar radiation in different parts, we can see down here in Antarctica, starting in late at the equinox, there's none. Antarctica is getting no radiation at the South Pole. However, look at Singapore, which is right near the equator, really doesn't change a whole lot. It actually changes probably more due to the rainy season than do the actual sun's change. At Brookport, New York, which is up more to latitude where we live, goes up very quickly, gets pretty powerful in the summertime, then drops way back off in the wintertime. So all that energy means that the Earth is getting it very differently depending on where you live in the Earth's. And you can see here the Earth rotating around the sun. It never changes its angle. It's just that it's pointed this way here. When it gets over here, it's still pointed the same way, but just now, where it is in relation to the sun, has flipped 180 degrees. So that here, the southern hemisphere is getting the sun, and here, the northern hemisphere is getting the more direct sunlight. So, with that, what happens to all this radiation that's hitting Earth? Well, part of it is absorbed. Part of it is reflected or scattered. Think about snow, reflective, lights sending back away. And part of it is transmitted into the Earth's surface. And it all equals 100%. So what is scattering? Well, you actually see it by looking at blue skies. That's part of the Earth's atmosphere scattering. But there's also clouds that would scatter. So when you have a dense overcast over your house, clouds are fairly white, especially the tops of them. It's going to reflect and scatter that radiation. Some of it is going to come down towards you, but a lot of it might move in all different other directions. So the amount of radiation you receive on that day is less than it would have been if you had bright sunshine. So therefore, that's probably why you might not be getting as warm. Reflection is another special case of scattering. And there are different amounts of albedo or reflection. Ice, snow, very high. Think about the water or a dark forest. That's absorbing a lot of radiation. It doesn't reflect as much. Then there are, up in the stratosphere, we don't want all this tremendous ultraviolet radiation always striking the Earth, or we wouldn't be living very well. We'd have a lot of skin cancer, uh, and a lot of other problems. So the stratosphere with ozone actually blocks, absorbs that chemical, has a chemical reaction that takes in that ultraviolet radiation and significantly reduces that amount. That's why there's a significant warming in parts of the upper stratosphere where most of the ozone lies. So here you can see solar altitude, how it changes from one, and you can actually see the reflection of the ice and snow here on this picture. And here it is, the totals. 30% is reflected by the Earth. So automatically you've lost 30%. Only 70% of the sun's energy makes it to Earth. Another 23% is absorbed by the atmosphere and 47% by the ground or the Earth. So that's your totals. And you can see, looking at the temperatures and how they change based on the summertime. Greenhouse gases, they're what allow us to live on Earth. If we didn't have greenhouse gases, most of more solar radiation would head back from the Earth out into space as infrared radiation, and the temperatures on the Earth would be a number of degrees cooler. So some greenhouse gases are important. They keep our temperature in line. What they are is they're gases that absorb infrared radiation. Remember, the Earth emits infrared radiation. So the ultraviolet comes through to the Earth, absorbed by the Earth. The Earth is heated. It emits. It's a black body, so it emits radiation back, and you go back as an infrared. These gases then absorb some of that infrared, and some of it is sent back to Earth, and some of it is sent out into the atmosphere, depending on how that gas is working. So that keeps our temperature slightly warmer. And the principal greenhouse gases, that's what? Water vapor is one of the most important ones. Carbon dioxide, huge. Methane is huge because it's really, really effective. It's 21 times more effective than carbon dioxide. So you don't need a lot of methane in the atmosphere to make a big difference. So one of the things too, with clouds, there's a lot of water vapor there, so they absorb the infrared radiation, or if the atmosphere is really moist, there's a lot of, even if it is sunny, clear day, a lot of the Earth's solar radiation is then absorbed by that water vapor and sent back to Earth. That's why at nighttime, a lot of the temperatures in southeast or in the areas where it's very wet don't get as cold as areas that are very dry. I'll show you that in a little bit here. There's another, what they call the calendar effect. This gentleman, the Keeling curve, designed to look at carbon dioxide. And you can see carbon dioxide oscillates depending a lot on summer versus winter. Because let's face it, it's the summertime in the northern hemisphere. You have lots of plants out. They're absorbing a lot of carbon dioxide. In the wintertime, you don't have as many. They're not absorbing as much, so it goes up in the wintertime. Now, these are the effects that we've now talked about. Just looking at some of this, I wanted to just look at California, very dry. Nighttime temperatures drop off into the lower 70s and the daytimes into the upper 90s. Same thing, we'll go down to Florida, very moist and high temperatures in the 80s, lows in the 70s, mid 70s. So there's not as much temperature change there due to all the moisture. So it actually works, what we're talking about. Finally, this infrared radiation from the Earth that's absorbed by different gases actually is utilized by our satellites, GOES satellites. What it can do with that is there are roughly 16 channels. There's a band 1 that looks at 0.47 microns. This is actually a blue light visible channel. Slightly different, 0.64 is more of a red light. We'll look at vegetation. It has a near IR of 0.86. Maybe look at a real high cloud. And you can see how each one of these has a use. And these are all based on different oxygen levels, different carbon dioxide or water vapor levels in the atmosphere that emit infrared radiation at slightly different values, different wavelengths, and it allows you to get a much clearer picture. We can look at low level water vapor versus high level water vapor. I can look at clean long wave, which would basically be all radiation coming out of the earth. It will show me the highest cloud tops because they're the ones radiating. I can look at other long wave or dirty long wave as it's called, or maybe even CO2 and see where the carbon dioxide maximums are. So it's interesting to look at all these different channels, 16 of them, and you can combine them and everything to get a better idea of what the weather is and understand how the radiation is being absorbed in different parts of the atmosphere. So hope you got something out of all this, and let me know if you have any questions.